Hello everyone. Let's start this assignment. So in this assignment, we have various tasks to do in R programming language. So I'm assuming that you have already installed R, but if not, then first you need to install the R. Okay, so this is the website. You can just search in Google for R only, and then you can download it from here, this CRAN project. And after that, for doing this project, you need to install the RStudio. Now, in various other IDs also you can use, but for this project specific, RStudio will help us. This you can download from the POSIT. Okay, so from here you can download it here. So just click on this download RStudio, it will be here, and then you can follow these steps, only the default steps. Okay, and then you can open this R. It will ask you some of the questions and just give next, and it will start. And also while starting the RStudio, you will have an option for 64-bit and 32-bit. There you select the 64-bit option. So I already have installed this RStudio, so I will not go for that again. So once you install the RStudio, it will look something like this, where here you will have the environment, then history, connections, tutorial, like that. Left side you will have the console. So this is very important part for our assignment. And right side you have some files, plots, packages, like that. So this also package is also very important for us. So for now, this console and this one, we will mostly focus on this, and slowly we will start this. So one by one we will do. So you can see here, clear workspace and history. So for that, what is workspace and what is history actually? So this will be your workspace for now, because we are not doing any kind of so we you have the option for scripts also, but in this case we are not going to use this script part. Everything we can do in console and RCMTR package itself. So how we can do that, I will go in depth on those part. But before that, this is your workspace for this assignment, and this is your history. Okay, so what this assignment is asking, first that install and run. So before that, clear workspace and history. So to clear that, this is very simple. You can go to session. If your workspace is like this, you have just installed and started working, then it's fine, no problem. But if you have given some of the commands and you have not closed that properly, in that case you can go to session, and then you can just click on clear workspace. You will have one option, include hidden objects and everything. Just click on yes, and this workspace will be, or this console will be clear. Next, for the history, go to history, and if you see something here, for example, in this example, whatever we are observing here, we don't have any values or anything. So in this case it is clear. But if you have something here, then you have this option here, that is clear all history entries. Click on here, and you will see one confirmation box. Just confirm it here, and the history will be clear. So before starting this project, you should clear both your history and workspace. Okay, then coming to this part, where many of us will face some of the problems regarding the installation and running the RCMDR package. So though this will need this we will need in later part of this assignment, but before that only I will show, so that you can start this assignment in a very convenient way. So there are various ways we can install the RCMDR package. The main problem that we can face, see, using command also you can use the, or using console we can install the packages. So before that, here also you can install. For example, you install here, search with the RCMDR package. This is the RCMDR package, and wherever it is installing, let it, and then install. So you can see here, it is downloading, and it already started. So let's wait for some time. But after doing this also, though it is also being installed with dependencies, we may face the problem. So how to solve that, we will see it here. But before that, let us see if this is working. If this is working fine, then no problem. But if not, then we have to do a console based installation that I will show. Even if you do it from console without the dependency, then also you will have some problems. Let's see. If it is running properly, then everything is okay. If not, then definitely we have to go with that. So once you install, then you have the option for library. Then in bracket we give the package name, and then so here see, the package is completely installed, and in right side you will see this RCMDR here. So I can click on here also, then it will be started, or else I can write even here that library, and then I can see here all the libraries are already coming here. So you can just select it from here. So RCMDR you can select it from here. We have given this, and then so most of us, what we will see, most of us will see that our screen is stuck here. It is not progressing, and even the RCMDR, uh, the main console for RCMDR or R commander, that is also not opening. In that case, what you need to do? That also we need to understand, because and also now while we are running this, see our history, we got here. So the main problem that everyone will face, that it's stuck here on the main process or the conventional process, whatever you follow, you will get one stop here. So how you can proceed with that? Let us first forcefully shut down this R, and the actual process we will now follow, because this one will not this will not open. So we will just close this. This will also take some time. So here actually nothing will happen. So that's why this is a problem. How to solve that? That we will do it now. Many of us will face the problem here. So 1 minute. Let me stop it from the task manager itself. You can also do the same. If it is not getting closed, just from the task manager, you can close the RStudio, right? So you can end task. Yeah. So see, it's closed. Again, we'll go to RStudio, and we will follow now this process. So in history, just see nothing is there. In console, I'm just again just clearing the workspace, that's it. And in history also nothing is there, then also I'm just clearing everything. Now we will install it from console itself. So for install, and we use as you have already seen, that packages can be installed from here or from other sources also. You can directly, even you can use R tools. But the main thing is, while doing this, you should for RCMDR, the main problem why it happens, because of the version mismatch. So what we need to do here, so we will give the name, that is RCMDR. So this is the name of our package. Then dependencies. So dependencies equals this one is true. So this is the command, that is install.packages RCMDR dependencies equals to true. So it will again start downloading some of the packages. You can see in history, even in environment, when we will start with the data set and with different values, we can see it here. Later we will see. Now let's try to start again this library, and then RCMDR, this one. Now let's try this. Let's see whether it is opening or not. Now you see this problem is solved, and you have this R commander ready now. So this is the thing, you have to go with the dependencies. Though we have used dependencies here in the packages section, here also we have used dependencies. See every dependency and everything, see here install dependencies, but then also it will not work due to the version mismatch. So for that only, you just need to run this command, this one, install.packages RCMDR dependencies equals to true, and then it will work. And how to open that? Just a library, then bracket RCMDR. Even you can open using this method. I'm just closing everything. Here also you will see RCMDR right side of your packages here. So just click on RCMDR, and it will 1 minute. So already it is, so just I'm checking, and again if I check, automatically RCMDR or R commander will open. So this is how we can open the R commander. Now let's again start with the assignment. Okay, so this we will close again, we will take it after some time, no problem. So here you can see already we have installed some values we have in our workspace. and our history also something is there. Just for the example, I am showing you how to do that. Clear workspace, include hidden objects, and so so as you can see, this is a fresh workspace. So this here environment is empty. Environment, this workspace is empty now. All the variables and everything got empty from here. This is a command that you can, when you will submit the R routine, you can delete unnecessary comments from here. For this session, see, environment is empty, and if you go to history, you can clear it from here. So just click here and you can see the history is also cleared. So that's how we can solve this problem, right? Okay, so now let's move to the first question of this assignment, and then let's go through the PPT again and investigate the PCMDR metadata. So this PCMDR metadata, it is actually our RCMDR metadata only, that we can check later. And this perform summary stats and create figures, we will see one by one. Then going to this instruction, answer the questions in the spaces provided. How we will do that, we can see here. 7, import the figures you create into PPT, and do not take screenshots. We will take images from there. We will export the images, and then we will import the images. Once you are done, change the title of this file like this. We will go with that, and then supporting R routines, how to create the R routines also. All these things we will see in this example. So now the first question is, create a vector name age with 18 age estimates. So there are 18 data, and we need to create one vector name age. Okay, so how to do that? We need to create one value, and then we need to assign this vector to that value. So we will do it in R. You can do it in R also, you can do it in RCMDR, wherever, no problem, but we will do it now here. So age we are creating, so we are creating age, and then the values we will take from here. So 1 minute. So these are the values, we will take it from here, and this, all these values should be separated with comma. So 1, 2. So we have to format it properly. You can also follow this video and just one by one you can do. So let me just draft this. This is a complete raw video. Even I will not edit anything here. Then you have all the codes and everything. So this will create a, and also in history you can check whatever. 1 minute somewhere. Okay, where is that? 41C, 34, 36, 37, 37, 30, 30, 30, 39, 40, 41, 42. Okay, here was 1 minute, no problem. Just one, we forgot to delete one. As I said, this will be a raw video. So yeah, see here, this is here, and also in environment you can see now age is there. So once you clear the workspace, this will be deleted. But for now, you can see in history whatever you have entered, and in environment you will see the actual value. So why we got this error here? Just because of this extra first bracket. Okay, no problem. So this has been created. Now this is only been asked here. So report the command you should to create the age vector. So what we have used? We have used the age, this one. So just copy it and paste it in your answer. So just paste it in your answer. You can paste it like this, you can whatever, like you just need to save this answer. That's it. So you can use it like this. So this is the command that we have given to R to create our age vector. That's it for the first one. It was very easy. Next one, report the command that calculates skewness in R. Make sure you include and explain all of the arguments used in this command. Now see, this one we can use E1071, that package, or else we can use moments package also. But for this particular question, we can skip the E1071 package because that package we may need in later part of this video. But for now, what we will do, we will use the moments package. So this because here it is not even mentioned that any types we need to use or not. So for this example, we can use the moments package. How you can do that? So first one is completed, right? Coming to next one. So here we have to so that's why we have to install the moments one. See here if already moments installed or not. So let me check. So yeah, moments not there, just we will install the package. So install dot packages, then we will give moments. So this we are going to install. So this has been installed, moments package, right? So the downloaded binary packages are in, it is here. Now here we will use the moments package. How we can do that? After installing from install.packages, you can use it in library. So library, and then you give the moments. So see library moments, and then moments, we have entered moments here in history. You can see one by one proper commands here and here. So we even don't need to check that, only environment is enough. So for now only values age has been created, no data set still here. Let's go, we will work one by one. So we have given the library moments, and then we need to check this skewness, right? In the question it has been asked that check the skewness of the age vector. So to check the skewness, we need to write skewness, and then we are doing it on age, and then na dot rm equals to false. So what is this? I will explain. So this is the actually arguments. So here if you see here, make sure you include and explain all the arguments used with this command. So what are the arguments? In skewness, we have given age and na.rm. So what these things are doing, we will explain it in the example only. We will show that. See, we have a skewness value here, right? So this skewness value we have to give, and then okay. So for this skewness, how you can do that? Just again copy it from there. So this is the skewness, and you don't need to include the install packages moments and library moments. You don't need to include all these things in your answer. So just give it here because this only been asked here, and just moving it a little bit. So here, and what it is asking is next, it is asking the make sure you include and explain all of the arguments used in this command. Now in this argument you have two things here. One is age, another one is na.rm. So I will just insert one text and I will explain what are these things. So here this x is, or this age or x, whatever we can mention, because anything can be here, any vector can be here. So this is the input vector for which we calculate the so here age, this is the input vector. So what we are writing here, this is the arguments. So in this particular skewness command, we have given two arguments. One age, another one is na.rm. So age is the input vector. It can be anything. So let's say it is x. So x can be anything, age, height, or whatever. Age can be any vector, any input vector on which we are calculating the skewness. So on which we are calculating the skewness. So this is one thing, and in this case we are using age vector with 18 values or 18 data. So this is the first argument. So this we pass in the first place on. Now second one is, if you see, we have used na.rm. So what is this na.rm? It is actually telling that in the data set, even any data, any of in the whole data set, for example, say we have a data set of 18 records, right? In this 18 records or observation, if any observation is blank or null, then also it will include that value in the calculation of skewness. So that's why na.rm is important, which is telling that it is a logical argument. So this I will write it like this, This is a logical argument. So what logic it is giving? Logical argument, why? Because this has a binary value, either true or false. So that's why a logical argument. In this logical argument, what we will pass? So that if it is false, so we were setting any values, the result will be, so it will take all the values for the missing values. It will take so here, as you can see, a logical argument I have already told that determines. So here the logical argument, true or false, determines whether missing values should be removed before calculation or not. So if we set it to false here, meaning if there were any na values, the result would be na. Since age has no missing values, this setting does not affect the outcome, because we can see here, because none of the values here are na or missing or null, so this will anyhow not affect, but we are giving this here. So this is the logical argument. It will take either true or false. This type of value it can only hold. So if it is false, then na values, the result should be na. We cannot skip the null values or false na values. All the values should be there in the our calculation. So these are two arguments we can pass in this skewness. Next, the third question is, use the R help to find out how the three skewness types 1, 2, and 3 are calculated in R. Which one is the default type used unless specified? Copy and paste the metadata for each type there. So for this one, as you can see, it is mentioning that skewness with types. As I already mentioned, the moments package, here the moments package, this one we have already installed here. Where, yeah, see, install moments, and we have used the library of moments. So to initiate that, this by default will use the type, but actually for this skewness we have three types. To see the types, we need to install another one package, that is E1071. While installing the RCMDR package, it is automatically installed, but again I will show you the command so that you can install if there is any issue, right? So I will show you install dot packages, and you have this install dot packages, and we will install E1071. This we will install. So this is already installed. No. So this is already installed there, so no problem. And then we will use this library E. So it's there, just use it. So it is there, right? So in this one, we will see what skewness is doing there. So for that, how you see the metadata from the R help, here you will get the help section, but we will go from the command itself. So question mark skewness, and then once you give that, you will have this here, just anything sample, you can see skewness, but for this question we will go with skewness. Here you will see that this argument, then x, anything it can hold, that we have already seen. In moments skewness, we only have x and na dot rm, the logical value indicating whether na value should be skipped before the computation proceeds. And the third one that is being introduced in E1071, that is the type. It is an integer between 1 to 3, selecting the algorithm which we are trying to calculate. So these three arguments we can see here. And what in the question it is being asked? In the question it is being asked that use the R help to find out the three skewness types. So already you have seen the three skewness types here. Three skewness types here. So see here, type 1, type 2, and type 3, how these are being calculated. This is already in the R help is there. So you can copy it from here, because you cannot take any screenshot. It has been mentioned in the PPT that you cannot use any screenshot. So you can copy it from here and you can paste it there. So mathematical formula, sometime you will have some problem, but you have to format it. In this video it will take so much of time if I just start formatting this here. So this is showing something like that. How you can do that? You can install, I'm just giving you one idea. You can install Notepad++. In Notepad++, first copy this thing there, or even any text editor which supports the UTF-8 format. Though this PPT supports the UTF-8 format, but while taking this from R to here, this does not, this is not working. So what you can do, any text editor you can take, and or even any online text editor also you can go, just paste that there, and from there you can take it here. So you can do it from any online text editor, even offline, but I will prefer the Notepad++. So you can do it from there. This is a very straightforward answer, so I'm just skipping this part because you can just take the answer from here. I have shown these steps here, that is question mark skewness. Then this page will open, and from there if you go below, you will have this type 1, type 2 and type 3 mentioned here. Now another one part is asked here, which one is default type used. So once we don't use any kind of type in this package, that is E1071, by default it will take the type 3. So this is I'm writing here because that one you can copy and paste it here, but by default type 3 will be there for skewness. If you don't mention anything which type you want to take, by default it will take now this skewness. But while doing it in moments, we don't use any kind of type. But once you install this specific package where skewness has 3 types, if you don't mention the type, from now on it will take the type 3 as the skewness. So, and another answer, I will just mention it here. For first answer, the metadata, all 3 types, copy and paste from R help. I have shown that how you can get that, right. So you can just take it from here, type 1, type 2 and type 3. That's it. Now coming to the next question, that is, so here now report the command that calculates kurtosis in R. Make sure you include the explain all the arguments used in this command. Again we have to go with kurtosis, and how this is working, that also we will see here. So for this, which command we will use, directly kurtosis only. So kurtosis again, in on which dataset we will use, on age. This is a vector just for example, and then na dot rm, again this argument also we will pass. So this is a logical argument, this will take false, and then we will have type. So we are using type as 3. Okay, so on kurtosis we are using type 3. You can see the kurtosis value here, just you can take it from here and you can paste it. And also again the same thing as you have explained the uh, arguments for skewness, the same we need to do it here. So the same we will do it here. So this, and then here you can see 3 arguments we are passing: age, na.rm and type. So this age is again numeric vector. I will just add it here. This is just one numeric vector. So 3 arguments. First argument is age, that is numeric vector. Second argument, we have this na.rm, which you can directly copy from the na.rm argument. We have given it here. So just the same, see, it is also same. And the type 3 or the type, this is another one argument we are passing. So this type is actually specifies the which type of kurtosis calculation you need. So which type of kurtosis calculation we need. So we are passing here, let's again go to the command. So in kurtosis we are passing age, which is having 18 records, na.rm equals to false. So if anything that is not having any value, that also we will consider. And then type is 3. So age is numeric vector, logical argument, and type is which type of kurtosis calculation we need here. Now use the R help to find out how the 3 kurtosis types 1, 2 and 3 are calculated in R. Which one is the default type used? Again here also we will use the default type as 3. If nothing we are mentioning, the default type will be 3. So which one is the default type used unless specified? If we don't specify, it will take default value as 3. Again whatever we have done for this skewness, the same thing we will do it here. So for specifically taking For example, see in moments also we have this. So to take this specifically from E1071, this package, how we can mention it here? So again, question mark means we are opening the help page. Then we are specifically mentioning that show me whatever you have in the E1071 package. So this package, and then we are telling that now I want to know what kurtosis is holding here. So we will see kurtosis here. So this is exactly what it is doing. It is taking kurtosis this function from E1071 package itself. So if we go on here, you can see kurtosis is opened here, and in bracket you can see E1071. But if you see here, I will just show you one thing. Where while we were installing this, kurtosis moment and skewness already marks from the moments package, and it came to E1071 already. So that's why whenever you will use the type default, if you don't mention anything, if you don't mention type, it will automatically go to type 3. So we have in kurtosis here, you can see the arguments x, na.rm and type. This also you can even write here. These arguments also you can take the idea from there, and you can write. And the metadata, this is the metadata again, type 1, type 2 and type 3, how these are being calculated, you can take it from here. And the again the same answer, unless it is specified, it will take the type 3 only. So I will just write it here. So again same thing, whatever we have done there. So first is you can take copy and paste from the rhelp. You can see here how we have reached the help page, E1071 kurtosis, and then type 1, type 2 and type 3. You can take the idea from here. Next is the default one. So I will just write it here. Default is type 3 if not mentioned. So you can write here if not mentioned. Now coming to this part, calculate the following summary statistics for age using R. So we are going to create the summary statistics for age using commands you found an RCMDR. So now in this case, we need the RCMDR package. So in this case now, RCMDR we will use, and how to do that for this particular part, we will use it here. And even while doing this skewness and even kurtosis, anything, so the process will be same, and we will use it with this, with the summary statistic, with the data. How we can do that? First let's do that. So for skewness type 1, so the we will just mention it here. So let's do it one by one. For skewness type 1, it will be very easy, but again doing that. So skewness, we have given the function skewness, and then on the which data we want age, and then which type you want. So we want type 1, and then because the first value you can see here, that is type 1, so we want this type 1, and na dot rm equals to false. So this is one, you have got this value, copy and paste it here. Next you have the skewness type 2. For type 2 we don't need to write the command again, just paste it with type 2 here. This is type 2, and this is the type 2 value. So this is the type 2 value. Next you have the skewness type 3. Again come here, and this is type 3. Take the value. Same way we will take kurtosis also, all the three types. Now again kurtosis type 1, type 2 and type 3. All this we need to take it from here. So kurtosis, again same formula we will use, that kurtosis, then bracket age, all the arguments we will pass. So kurtosis, then first argument age, then we are mentioning type equals to 1, and then we are mentioning na dot rm equals to false, just for the all the arguments. So this is the first value, we are taking it here, 1.383604. This is your first kurtosis value. Kurtosis type 2, take it from here. This is type 2, type 2 kurtosis 2.2871. And you can skip all this. If you just want to see these steps, you can skip, or if you are watching this then from first to last, then also okay, no problem. So here type 3, So this is type 3 value, 0.91 something is written here. So this is type 1. And now coming to the right part, summary statistics. Uh, in this one, how to use that. So now we will initiate the library of RCMDR because we need this now. So from here on, this R commander will be used extensively. So we are now using the library, or even as I already told, you can go it from you can take it from here, RCMDR, you will get it here, RCMDR. Okay, so it will open the RCMDR package, or even click on here, packages. 1 minute, I'll just close that. Close that, and again opening from here. So RCMDR open now. It was already open, I closed that, that's why it was not opening. So what I did, I just closed the package from here, this small tick, and again I just tick given the tick mark here, and the R commander already opened here. We'll just minimize it because in the R commander currently there are no active datasets. See, when I clicked on the dataset, there are no active datasets. So on the vector, that vector we need to convert it to dataset. So how we can do that? Let's see this part. So we will create a data frame or dataset, whatever. So HDF, we are creating a data frame. So what it is doing, it is taking the data dot frame. So data dot frame where age, we are giving the age. So see now, the 18 observations and one variable, that is age. Now it has been created. You can see the values here. Just closing it for now. Now if you go to R and click on here, you can see the data set age underscore df data frame. We are clicking on OK. So we have selected the age df here. So that's how first from the values we need to create the data frame. Then that data frame or data set we can use in the R commander. Now what in this particular question, what has been asked, summary statistics calculate with RCMDR. So we need to calculate the skewness and kurtosis. How we can do that? Go to RCMDR again, in statistics, summary, then numerical summary. So then first statistics, summary, then numerical summary, and then click the variable or click the data set that you have. Then in statistics, we need only skewness and kurtosis, right? So we will just give skewness and kurtosis and type 3. We don't need quartiles also for now. So just click on OK. This is one command that is already given in R script. Just go to your R, and here you will see what are the values here. In the R command, R console, you can see. So what we did here, we just clicked on the statistics. Again, I am showing you. Then numerical summaries, then age, and then statistics, skewness and kurtosis. Then click on OK. It will fetch from the here to, it will show you the console values. Here you can see on the RCMDR we got the value skewness at 0. This one, just copy it from here, and in the skewness value paste it here. You can see here skewness we have calculated from command, and skewness we have calculated from RCMDR type 3. Both are same. It should be same always, it will same only. Then you have the kurtosis value also. So this is the kurtosis value. So this also we will paste it here. Now so which type we have used? We have used the type 3 only, right? So just write it here that we have used the type 3. So this is type 3, and this is also type 3. That's it. This is also completed. Coming to the next part, that using RCMDR calculate the following summary statistics for age dataset. It is telling us to calculate mean, standard deviation, standard error, IQ or quartile, CV, and 5 quantile. So how we can do that? Again, we will go through the numerical statistics, and we can do that. So just to go to the numerical statistics, and whatever mentioned we just have to select it here. So statistics, then summaries, numerical summaries, then here age, and then on statistics you select whatever mentioned in the question. So first it is SD, that is standard deviation here, then AC, standard error of mean, then we have IQR, so interquartile range IQR, then we have CV. So this CV one, it will not work, but okay, let me show you how this will how we will calculate this one. Then coefficient of variation, and then 5 quantiles. So these quantiles we will tick it here, and what are the values? That is 0, 25, 50, 75, and 100. So 0, 0.25, 0.5, 0.75, and 1. Just I am clicking on OK. So to calculate this CV, we will use the mean and the standard deviation formula. So here you can see the mean is not there. So you will just go to the statistics, and then summaries, numerical summaries again. Then in statistics, we will enable this mean option, and you can see now here we have this mean value, standard deviation, AC, IQR, all these values are here that you can represent in table format, as I have already mentioned. So here what you can do, standard deviation divided by mean into 100%, that will give you the CV value, because you can see CV value is not coming here. So how you can do that? It's very simple. You can just give this formula, that is this one, this ST. This ST we will just divide it by this one, 39, that is the mean, and then into 100. So we have this value. This is your CV value. So how we are doing this? Just remember this thing. You will select all these things in the statistics. In summaries you will select, so this is the active data set, no problem. So you will select here, then summaries, then numerical set. In age statistics you select mean, standard error of mean, coefficient of variation, standard deviation, in interquartile range, and then this quantiles also. But remember, if you even if you see select this coefficient of variation, this is not coming. So what you can do, you can manually calculate this one, that is standard deviation divided by mean into 100, which will give you the coefficient of variation that we have calculated here. Now this you can represent in a table format in your answer. So just create a table, and you can just so here mean 1, 2, 3, 4, 5, and then 5 quantiles. So you need a 10 cross 1, 10 cross 2 table, and in this table you can just give mean, and then ST, standard AC, IQR, CV, and then 0 to 100, this percentiles you can give here. You can take all the values from here, from mean to this 100 percentile you will take it from here. But for CV value you just need to give SD by mean into 100% or 100, and just take the manually calculated value from here. So this is how we will be doing this exercise for 2A. Now coming to 2B, using RCMDR, make a histogram and a density plot of age using Gaussian kernel and the default settings. Please paste both figures below. So from here the figures part, this is getting started. So let us do that. So this is also very similar. We will do it from the RCMDR package only, or RCMDR commander. We will use it here. So for graphs we will use, see how we can do that. From the commander only we will do that. So in the commander again, you can go to graphs, and in graphs you have histogram here. Click on histogram, and you need to select which variable or which set you want to use. So here we are going to use the age one, and in the options you have this frequency counts, percentage, and densities. For now we are using the frequency counts here. So in the frequency counts, what are the what is the x-axis level and y-axis level, like that we have to mention, and then we have to go from here. So in the x-axis we need the age. So in x-axis we are providing age, and in y-axis what we are calculating, we are calculating the frequency. So we have given here, and what is the graph title that you want to provide, whatever what you can give anything. This is age histogram. So this is the age histogram, and I'm clicking on OK, and you can see the age histogram is created here. So how we need to import this? Just here you will have file, then save as PNG, and in documents I'm just save anywhere, no problem. So I'm just giving age histogram. So this is age histogram. I'm just saving there and closing. And this histogram we need to import it here. Insert pictures, this device, and then documents, age histogram. We have imported it here. You don't take any screenshot. So just take the images like this. And again, next what it is asking. So what this question is asking, see, density plot of age use Gaussian kernel. So how we can do that? Again, go to R Commander. So again, go to R Commander, then you go to these graphs, and then you have the density estimate. Click on here, again select the variable age, and then option. In this option, select the kernel option, and in kernel function should be Gaussian. And again here you need to give the x-axis and y-axis values. So in x-axis we have age, and in y-axis we have density. So this is age and this is density, right? This is also done, age and density. Now click on OK, and again our this density curve is ready. So for this density curve, so both these curves are ready. Again, you can go from here, file, save as, and you can add one thing here. You can see in the density curve, we don't have the main option here in the in the here in graphs. In density estimate in options, you don't have the main option, which was giving us the graph, or the graph header, or the graph title. So how you can do that? That's very simple. Again, just take this code, or just from here, if you see, we have a main equals to age histogram like this here. The same thing we will use here also. Just take this density plot, paste it here, and use comma, and give the main code from here. So main age equals to histogram, take it, give it here, and this is age density. Now select the whole code only from here to here, and then submit. And one thing here, so some age density we have to give the yeah. So this is age density, and we can use it like this. Now you see, you have the graph title also. So from the conventional method, in the graphs you don't have the main option where we are giving the graph title, but from the from taking the comparison from histogram, we can use it in density estimate also. So you can use the age density as a graph title, or whatever you want, you can use it from there. Again, save as png, and give it as age density, save it. And in age density, just take it from here, insert picture, this device, we have age density here, just align it here. So this is how this question is also completed, done. Now we have the next question. Do the histogram and density plot of the age dataset look like normal distributions? Explain why or why not. So we need to check this age histogram and age density, and we need to tell whether this is giving any normal distribution or not. So for that, we will use the test of normality. So test of normality, what is this? We will test based on the there are various methods we can use. So for this, we will use the Shapiro weak normality test. There are lots of tests we can perform, but for this one we will use that, and we will match the that normality test with our result. We have already two results, one is histogram, another one is age density. We will match the normality test data with this histogram and density. So how we can do that? For this, we will go to again RCMDR, and then here in the statistics you will have various options again. So in the summaries, you will see the test of normality. Click here, and there will be, you need to choose the variable that is age for us, and then normality test. We have Shapiro Wilk, then various options are there. So we will go with this one, clicking the OK, and in the R command, you will get this value. So data age, where W equals to 0.92879, P value equals to 0.1849. Now regarding this thing, when we use that, so test of normality, so the histogram and density plot do not look like normal distribution, this due to right skewness. If you see the graph here, so this particular graph, even if you properly see here, so this histogram and density plot both do not look like normal distribution. There are some right side skewness here, and kurtosis also, we have a kurtosis value of 0.91, and then so that's why now is it matching with these values. Let us first take the values here. So these are the Shapiro-Wilk test, or these are the normality test values. Okay, these are the normality test values. We are taking it in the R platform, or just giving it like this. From here to here, we will just give it. This is normality test, and in the normality test, these are the values that we got: W value and P value. Based on P value, we can consider whether what is this thing telling. So this is the test values that we got. So now we will check whether what's happening here. Just one moment for the alignment. So you can format your page however you want. Just yeah. So already we have seen from the previous images that it is not looking like a normal curve, or it is not looking even like a normal data due to right side skewness of the particular graphs. Now coming to here, this particular p value, this determines something. So this test result, where we have the p value like that, this shows if a p value is greater than 0.05, so we will fail to reject the null hypothesis of normality. However, this does not confirm the data is normal. It means there is insufficient evidence to conclude it's normal, likely due to the small sample size, that is n equals to 18 only. We have only sample with 18 samples only, so reducing the test power to detect the deviations. So though the p value is greater than 0.05, which indicates a normal distribution, but then also it is a very small value with a very small sample size, so that's why we cannot conclude that. So that same thing you can write here based on p value, and also from observation from the graphs, we are determining that though we are not able to reject the hypothesis, but also we are not confirming the hypothesis that this is a normal distribution. Sorry. So in that case, what we can write here, so this normality test also is, it is telling us that a p value of greater than 0.05. So here we are getting p value 0.1849. So p value is greater than 0.05. We can see here. So we fail to reject the null hypothesis. Sorry, yeah, we fail to reject the null hypothesis. So we fail to reject the null hypothesis. Previously I mentioned we are not able to reject, but yeah, actually we fail to reject the null hypothesis, which is telling that no, it is not normal. But though it is greater than 0.05, so we fail to reject the null hypothesis, that is h naught. We fail to of this normality test, but we can see from the skewness values and the curve that it is not normal. So due to this very small sample size, we are not able to confirm on the normality. Though it passes, not even passes, it just marginally passing, but then also though it is passing, due to very small sample size, we are not able to confirm on this normality. So we fail to reject the null hypothesis of normality. However, this does not confirm the data is normal. It means there is insufficient evidence to continue or conclude if it is normal. So we have insufficient evidence to say this is normal. So that's why we are not able to confirm on the normality, though the p-value is greater than 0.05. So this is one thing. This is the question. You can just write it down as already we have spoke. So you can just continue writing on that. So Shapiro will normality test we will do based on the test value, p-value. We will compare this with age histogram and age density, the curves that already we have created, and then we can confirm on that. Coming to question number 13, distributions of random variable. This one, in this lab, we will investigate the normal distribution first. We will use the graphical tools of R to assess the normality of our data. Then we will learn how to generate random numbers from a normal distribution. We will work with a data set of body measurements from 247 men and 260 women, considering considered healthy young adults. So for this 3A, what we are going to do, we will be using the BDIMS dataset. So what it is asked here, that how large is the BDIMS dataset. So this one, for this one we need to install a package. Let's go to again our console. We will install the package. Remember, whenever we are installing a package, we will use install.packages command, and you can take the package from the right side window, or even you can take the package from here also. So that's not any problem, you can take it from anywhere. So let's complete this. So we have to install.packages, and we will use open intro. Then yeah, so it's getting installed. Then we will open this. So it is installed. Then library, open intro. Let's open this. So everything we have opened here now. Next, we will use the how many observations or whatever we have. Let's take the BDIMS, this data set. Here you can see 507, here 507 and 25 values or variables. So what we have here, what it is asking, first of all, see here 247 men and 260 women. If you add that, you have 507 only. So this data set has 507 observations and 25 variables or columns related to body measurement. So how large is the BDIMS data set? So you can take it from here. Just take it, take the screenshot, not screenshot, sorry, take the copy and paste it here, and just write a single line that yeah, it's containing uh, 507 data and 25 variables. So 507 observations and 25 variables. So that's the this is the so question answer. So how large is the data set? So this is the answer. Now you can write here that 507 observations and 25 columns or 25 values or variables. Okay, so here 507 observations and 25 variables related to body sorry measurements done. So this is the answer for your 3A. Now coming to 3B. So in 3B, we will be observing various things again. So in the 3B, we have to see, since males and females tend to have different body dimensions, it will be useful to create two separate data sets, one with only men, another with only women. Next, make two separate plots of men sites and women sites that illustrate the frequency distribution of these two data sets. And you can create two stacked plots using a single command in RCMDR. So in this question, though it is telling us to create the plot, but actually we don't need to paste it here in the answer sheet. Then it is asking that, the question is asking, explain how the male and female distributions differ by describing the summary statistics you can observe in the distribution plots. Be as specific as you can. So we are going to answer this question. For this, we need to see the data first. So how you can see a data on this data after installing all these packages and everything? We just need to give data, and then our set name is this one is our name, and you can see this is the data. So this is how the data is there. You have the height, then see height, then sex, weight, age, all these columns you have, and this is the sample data that we have here. And we need to verify value. If you want to verify these values, you can use it like this. You can verify. So see, these are the 25. So here how it is working. So for males and females, what are the sex values given? So 1 means male and 0 means female, like that. So if you come here, it is saying that since males and females tend to have different body dimensions, and even in the data set you will find male and female with different sex values, it is given by 0 and 1s. So zeros and ones you will get it here as integer. Only two integer values are here. One is 0, another one is 1. We can use that value to calculate the number of males and number of females. Now, so already done, and then in bit. So now we will do with this comparison again in here our commander. So here in dataset, now we will see this BDIMS option. This is now here. Previously we were working with age data frame. Now we will work with BDIMS dataset or data frame. So just selecting this data. Now our dataset is selected to BDIMS, right? So now in the active dataset, we will create the subset of the active dataset. Now we will create the subset of the active dataset. How we can do that? Go to data. Now in this data, you have the active dataset option. Now here you will have the subset active dataset option. Here in which where you want to do the subset. So we want it based on 6. So based on 6, we want to do that. So if it is 0, we will give it women. If it is 1, we will give it men. So, and then subset expression, you need to mention the subset expression. So subset expression is if 6 equals to 0, and name the name for the new data set. So this new data set name also you can provide it here. So based on that, your two data sets will be created. You can name it as fdims and mdims, or we can give it like this, male or female BDIMS. So you can give anything. That's for example female, and like this. So this is how you can perform this, no problem. So this is the option that we need to remember, that how we are going to fdims, or even we can go with fdims and mdims also. Let's name it as fdims. So fdims, so that is bdims body dimensions, and here fdims female dimensions. So here we have given where sex equals to 0, and this is selected at 6. Creating here, you can see here fdims is created. Fdims we have see 260 rows and 25 columns. If you come to this question, you will see that 260 women are there. So already, so successfully we have created a subset of our whole body data set. Now in the same way, we will prepare the male data set. So again data, then active data set, then from here select active, so here sorry, subset active data set. Again based on sex, we will define the mdims male dimension. So 6 equals to 1, and we will name it as mdims. Any particular name you can given, there is not any problem. So just before doing that, just remember what are the name you are giving here. So we are giving mdims, that is subset of bdims, and where 6 equals to 1, you can see here. Clicking on OK, and again Nani, we don't need to cancel this. So here you have 1 minute where subset, so okay, sorry, we have mdims here. We need to click bdims before creating the see here. This is also a very good example. We were in the fdims dataset. In the fdims dataset, do we have any sex value equals to 1? Obviously not. So that's why it has created 0 rows and 25 columns. Because of that, now we will rewrite it again on the bdims data, because this is the master data. We cannot do it on fdims, because in fdims the sex value is 0 only, and we are trying to extract 1 from there. So that's why it was not working. So again, coming to data, active data set, then subset, and here we will select again sex, and then we will give sex equals to 1, and then we will give it as mdims. Okay, override the data set. Yes. Now see, on the so the bdims definitely has 507 rows and 25 columns. Now here fdims having 260 rows and 25 columns, and mdims is having 247 rows and 25 columns. You can confirm it from here, 247 men. So we have successfully created two data sets based on, or two sub data sets based on the values of sex, 0 for female and 1 for male. So that is completed. Now coming to this part, what it is asking, we will exactly answer that part. So it is asking that we have to create a stack plot. So here, hint, you can create two stack plots using a single command in rcmdr. We will definitely use that. But normally, if you go with the plot section in the graphs, and then first of all, it is asking us make two separate plots of male sites and women sites and illustrate the frequency distributions of these two data sets. So we need to go with the frequency counts, and then we need to plot two separate plots. On a same time, we need to plot two separate graphs. So how we can do that? If you go to in the graph section in the histogram, here if you see, even if you try with plot by groups, so I don't know, for this specific version this was having some issue. So we have created uh, like we can do the same thing with the commands. Let me try with the commands here, and the same thing you can also try here. So we will create the histogram based on that. And so the histogram, this is for this part, and you don't need to import this image in the ppt, but you need to create one observation from this images. So histogram, we will create it so that we can get two subsequent graphs at a single time. So hgt histogram, then which factor we are using? So the factor here is 6. So based on the values of 6, that is 0 or 1, we are going to send which data set we are using. Data equals to bdims on the whole data set. Then breaks we will use, that is Sturgis. Then the color will be 1 minute. Then the color will be dark gray or whatever color you prefer, because you can give anything, that is not any problem. That x lab equals to height, and we are calculating all these heights in centimeter. Then y lab equals to, we have frequency, so we have frequency in y lab. Then we have type, we are counting the frequency equals to type. You can see the same thing in command also. So type is count. Then layout equals to c 1 comma 2. See, you don't need to put this graph, but for the understanding we need to create this, because this is also important. Otherwise the observation will be not that much correct. So then, or even you can just generate it in a single term, and then again first for females you can generate the graph, and for male you can generate the graph, that also okay. So that is strip. equals to strip dot custom, where factor dot levels equals to C. So here we are creating two part, women and men. So this we have created. The command, there may be some parenthesis problem or something like that. We can see that. So we are submitting it here. Error, we have one error. I think something in the writing part only. Let me check again. You can first forward this video, no problem. So let me check once here. Histogram. Then we have this HGT factor 6. Then data equals to BDIMS. Data equals to BDIMS. Then comma. Yeah. See here. Breaks equals to STURGS, correct. Then called gray slab ylab, correct only. Now it is, there was one dot instead of comma, so no problem. Again we will give it here, and once you give it from the RCMDR commander, just select and submit it. So maybe histogram, I just created this function, this not option. 1 minute. If we just histogram, I just created his. So we can see here it is showing us that histogram could not find the function histogram. So for that we need to install one package. So that package is lattice, or we can introduce the package lattice. It is already installed. You can check it here whether it is already installed or not. So here we will see the lattice here. So let us if that is installed, then it is okay. If not, we will install it. So library, and then see here lattice is already there. So we will just take it, and we got these things here. Then again we will run this histogram. So we will run it here. You can do from that command also, there is not any problem. And now we can see here we have men and women, two uh, graphs in a single plot with frequency and height. We have that now. Here you can see the height from here, frequency from here, and you can see the frequency here, and you can see the height here. So this is how we can perform in a single command. We can use two plots. So yeah, so you can see here in a single plot we can use two subplots with this particular command, but for that you need to install the lattice. Okay, so now that when we can see that, now to do that we need to do one more thing here, that is we need to understand the question. See the question here, what it is asking. It is asking that, so hint, you can create two stacked plots using a single command. So we have done that using lattice. Explain how the male and female distributions differ by describing the summary statistics you can observe in the distribution plots. Be as specific as you can. So now coming to the summary plot, this has not been asked to implement these plots in the answer, but you can just like write, or you can just from the commands itself you can take it. So the screenshot is not needed, even the image also not needed. So for this one, the primary difference, even to understand this difference, what we will do, we will create a separate statistics from here. So first we will select the mdims or fdims, no problem. So we have selected the data set as fdims. In the statistics section we will go, and in the numerical summaries, in the statistics part we will take mean, standard deviation. So we will do the graphical analysis also, but to match it with proper perfection or answer, we can use the numerical summaries also or numerical statistics also. So what are the important values that we need to understand about these data sets? So we need mean, we need standard deviation, we need interquartile range, and we will use the quantiles from 0 to 100. And then we send it, 1 minute, we must select a variable. So for our case, what is the variable? That is height. What we are doing here with the height values, height centimeter. So I have not selected that previously. So again statistics, then summaries, then numerical summaries. We will need to select height here. Then in the statistics we have mean, standard deviation, interquartile range, anything type 1, type 2, type 3 doesn't matter because skewness is not there. So then we have just, for example, selecting type 3 because it will be by default for skewness and kurtosis if we don't select. In the quantiles we have 0, 2.5, 0 0.25, 0 0.5, 0 0.75 and 1, that is 100%. Clicking on OK, you have the data set here. The same we will do with the male data set, MDIMS. OK, then again statistics, then summaries, numerical summaries. Here again we will select the height, and in statistics all these options, and here. So these are the two values we have now in this section. So if you see here, we have selected all the quartile values and everything. So now it is asking us that what is the interpretation or what is the thing that we are doing here. So if you see here, the primary difference from these two, just why we are using this numerical summaries also, we will understand the concept from numerical summary and we will compare it with the image that we have generated. So this is how we can compare the both cases. So the primary difference is the center. Main sides are 13 centimeter higher on average. So on average main sides are 13 centimeter higher. Okay, how we can do that? On average, you can see this is the MDIMS and this is the MDIMS. You can see 13 centimeter higher, main sides are 13 centimeter higher. In the image, if you are trying to observe, you can see this small spike is almost about 13 centimeter. So the average is almost 13 centimeter. Not only the specific small, I'm just giving one example. From here you can observe this mean. Then also, with the main histogram shifted to the right, peak at 175 to 180 centimeter. So you can see the main side, the main peak is almost on inside this 170 and 180, whereas the female peak is on 160 to 170. So is it matching with our data? You can check it from here on the 50% data. The 50% it is on 164.5 and here 177.8, which is exactly again matching the graphical representation. So we can say that yeah, this is also confirmed. So this is why we are taking the numerical summaries also as well as the graph. Both we will correlate to understand what is happening, and then we will give the answer. Then main sites are slightly more spread out, wider range, higher standard deviation. So check this standard deviation also. For males, this standard deviation is 7.18, and for female, this standard deviation is 6.54, which is again showing that the male sites are more distributed or more distributed rather than the women. And their histograms are slightly more pronounced right skew with a few outliers. Both distributions are roughly bell-shaped, with women's being flatter, broader peak. The women's distribution is slightly more symmetric and has fewer extreme values in the right tail. As you can see, this is a more systematic and this is more spike value. So these are the observations. You can just replay this video and you can note these observations and write in your answer which has been asked here. So I'm just mentioning this answer like this. From comparison, uh, we can get this. First is take the numerical summary and then take the second, in the second option, compare it with, and then compare it with our histogram. Then write it here as you understood on the standard deviation, on the mean, then based on the range where the spike is there or the highest value, that you can take from the even you can just replay this video and you can note it down. So we're not going to that part mostly. So see, one part here, we have previously created fdims and mdims. You can create any vector, no problem, that's not any problem. Coming to here, so here it is asking for fdims and mdims. That's why already we have created fdims and mdims, but you can create any vector. But in that case, again you needed to create another vector for this question number 3b. So now let's solve this question number 3b. So till now we have solved question number 3b, but yeah, this is also just continuation of this 3b only. So what it is asking, that in your description of the distributions, did you use words like bell shaped or normal? It is tempting to say so when describing unimodal and symmetrical distributions. However, to determine how accurate that description is, we can plot a normal distribution curve on top of a histogram to see how closely the data follow a normal distribution. This normal curve should have the same mean and standard deviation as the data. Let's do the for the women's data. So in this question already, for women data or for female data, already the values are created. The same thing we need to follow for males. So the actual exercise is 15 number slide, 16 number slide, and 17 number slide. We need to combine all these three. We need to combine the knowledge of all these two, and the same knowledge we need to apply in slide number 17. Use the same instructions to make a plot of the male heights and overlay the corresponding normal distribution. Before coming to this part, we will observe whatever written in these two slides. So first we will create this FAGT mean, and let's see if we are facing any error or not. Just copy it from the slide, and you can do it from R Commander, or you can just closing this for now. This is not needed right now, or even you can do it from the console. So anything is fine. Now once you give that, see FAGT mean, female height mean, it is here now. FAGT mean, that is here now, and you can see the value here also 164.8723, where here also 164.8723. This we have created from the RCMDR. This we have created from here on the FDIMS height. FDIMS is the data that we have created here. You can see 260 observations, BDIMS 507 observations, FDIMS 260 observations, MDIMS 247 observations. So FAGT mean is created. Now what has been asked here? So mean has been created for female height. Now we will create the standard deviation for the female height, and we will assign this value to a variable or something, whatever value, whatever you say. So we will give it here, and so what it is creating, see, if AGT female height standard deviation 6.54, match it from here 6.54. That's why we have created this numerical summary before coming to the 3b part of the next part. Now what it is asking, so in this slide these two are created. Now here if you see, next we use these parameters to overlay normal probability curve over the density histogram. We use two functions. dnorm creates the normal distribution and lines plot the continuous distribution. You can copy and paste the 4 lines in one command or line by line. So you can paste all these 4. We will be going with line by line. So as the question instructed us to go, so this is the histogram for FDIMS height probability equals to true, giving it here. And so let's see which graph has been created. So see, histogram of FDIMS height, where this is FDIM heights and this is the density. This graph is created here. Now what it is asking here, again the same thing we will follow. So it is asking that to assign 140 to 190 this spread value to x, that we will assign it here. one by one we will perform in the console or even the script in R commander, any place you can do that. When we created this X, see, this has created 140, 141, 142 type this one vector here on the integer level. Now coming to which is holding 51 values. By the way, you can take the sample example. Age was having 18 values, X is having 51 values. Now third one is Y denorm. We will see this Y denorm. So again we will push it here, and you can see Y values are here also. So this is also created here, which is on the edge mean and standard deviation on the normalization. Now lines. So we will be taking the lines also, this code also, and we will see what it is creating. So enter, and if we come here, we will see one standard normal curve is on the line curve, or the line curve on the histogram. So we got this. A normal distribution has been created. So based on my screen resolution, it is showing something there. That's not any problem. So this is what we use with our code. Like we can use this normal. Now this is already, if you see here, this is already the next slide. Now we need to do the same thing for the male dataset. We have done this on the female dataset. These two numbers, slide number 15 and slide number 16, both these are done on female dataset. Now we will do it on male dataset. Okay, so now to understand this, what actually we have done, so just I will go through this what we have done here. For this hist command, what we have done here, it creates a density histogram where the total area of the bar sums to 1. And for this X value, this X 140 to 190, what it is doing, creates a sequence of X values from 140 to 190 centimeter, covering the range of omen sites, which is 147.2 to 182.9. Then Y denorm computes the density of a normal distribution at each level. This denorm, this creates a density, this, this one computes the density of a normal distribution at each X value using the mean, that FHGT mean and SD, FHGT standard deviation or SD of the omen sites, and lines is plotting that. So this is how we do that for females. Now doing the same thing, we will do the same thing for males also. So for this one, we will create already we have created the MDIMS. Now we will create the MHGT mean. And so how we will do that, this is also very simple. We will just cover it. So we will create another one value for MHGT mean, where we will take it from the male data set, that is MDIMS. That's how it becomes very convenient if you use this kind of naming conventions. So now you will see one MHGT mean is created here, 177.74. Compare it with here 177.74. This mean that is on MDIMS data, males data set. Now coming to MHGT SD. So this again we will follow MHGT SD. So, and also before that we will close this female data set here. Now this is also created. Now we are giving enter. You will see another one, sorry, this is F here. We just need to modify it with M. So MHGTSD on the MDIMS data. So on the MDIMS data we have created. Now giving it here, you will see MHGTSD. This value is also created. On the next step, now here one thing, for the female data set we have taken 140 to 190, but for the males data set, for the male data set we are going to take it from 150 to 200 based on the scattered values of the males data, because we have a, in a 100% value we have a 198.1. This value also we have 198.1. So that's why in the first example, when we have taken the female data set, we have taken 140 to 190, but in this case we will take it from 140, so in this case we will take it from 150 to 200. Okay, so we will take it from 150 to 200 to cover all the values. In the first example, it was easy for, like, not easy, it was just we're just taking 140 to 190 because the maximum 100% we can see here 182.9 for females, but for males we can see it is going up to 198.1. So it is convenient to take more than that value, that is near about value is 200. So once we take that, just we will take it from 150 to 200, which will be capturing all the 0% to 100% data. So we are just now see this x value here. It is starting from 150. Once I initiate that, it is starting from 150. Previously it was starting from 140. Now it is starting from 150. It just got modified. Now on the y data, this y also we need to modify based on the male data. So this one also we need to modify. So where x equals to x, mean equals to, this is m AGT mean, and is standard deviation, this is equals to m AGT SD, this is y. So we just need to give it here, and this y also created. Now this lines, this is just as it is, same, no change. We are creating here, 1 minute, plot.u has not been called yet, 1 second. Y denom, so lines color equals to blue, histogram HIST, okay, histogram is not called yet, so no problem. So histogram we just need to call it here, histogram mdims, probability equals to true, histogram is called here. Now we will have it here, histogram here. Then again sorry, already see the values are already present here for 150 and this y value, so no problem. Just we will again just give this command on y, and then we will plot it, the line also normalization or normal, that also we will draw it here. And now you see there's a very like smooth normal curve we have on our male dataset. So now what we need to do, we need to save it, because let me check once whether it has been asked. It's the same instructions to make a plot of the male heights and overlay the corresponding normal distribution. Report the commands you use to generate the plot. So what you need to do first, you need to go with, so see, already we have created the MDIMs. So if you are creating MDIM in this particular step, include the MDIM step also in your answer. Otherwise you can start with the MAGT mean from here only. You can start it from here, no problem. So we can use one by one, or you can take all the 4 commands, and you can that is, if that is convenient for you, because I'm just, what I will do, I will just make this change directly in my PPT, but because here histogram was taken later, so you can just do the same, or you can do it anyhow, we have already seen the result, right? So this is here, and then you have this one, FAGT min, yeah, and then histogram, this hist is here, so this histogram, and then we have this x, and then we have, yeah, 1 minute. So these commands we have filled, just we need to edit it. So this y, and then lines, yeah. So this all are for female data set, but whatever we have done there, we can do it here also. That is for males, MAGT min, and that is on male data set. Then MAGT SD on standard deviation on male data set, and histogram on male data set, probability true. Here we have modified it to 150 to 200. This we have done, and then both these are same, but for this case this was m HGT mean, and this was m, let me check whether this has been updated. Yeah, m HGT mean, and yeah, so we are done here. Mean we have already used, let me check what we have used on mean. Yeah, so y denom, mean MAGT mean SD equals to MAGT SD, and then this one we have used. So this is how we can use that. Now is the plot is, yeah, to generate the plot, paste the plot. So how we can do that? Coming here again, the same thing, save as PNG, and here we will give it as no mdims norm. So we will insert this mdims norm here, insert this device mdims norm. So this image is here. So this is how you can paste your images for the answer. Sorry. So this part is also completed. Coming to next part, report the summary statistics for the male and the female weight datasets. To receive full credit, briefly explain why you selected each of these statistics. Now what it is asking here, till now we were working on the height, right? So now we will work on the weight. So now we will be observing how the dynamic data it is changing based on weights. So to do that, we will select some of these statistical values, and it is a very again simple. We can do it with RCMDR or R Commander. What we need to do and how you will create this, I will just give you one idea, and it is very simple. Just we need to copy and paste, and why we are selecting that particular statistical summary object, that I will explain here. So what we are doing, first of all, go to just this one already we have taken, so closing that. So what it is asking, it is asking us for the weight distribution or the weight related values. So again from RCMDR we need to do it. So in the RCMDR we need to do it using the weights. So in the comparison table, mainly what important part will be now to consider the weight. So again statistics, then summaries, then numerical summaries, and here we will select the weight, that is WGT. Remember this is very important. Now here if you select HGT or something else, it will be very different, or even if you select sex or anything else, that will give you some different result. Here we need this specific thing based on weight datasets only, so we will click on weight variable. Now click on OK. So okay, here also see, report the summary statistics for the male and female weight datasets. So first we are selecting the MDIMs, males. You can do whatever, like you can take on female weight, you can take on male weight, no problem. So based on that we can perform that. Even you can take it from the dollar signs, from there also you can take these values, so that will not create any problem. But let's start with that. So here statistical, for this we are first selecting the MDIMS dataset. Okay, statistics, summaries, numerical summaries, we are selecting weight here. In the statistics form we are using mean, standard deviation, then median. uh, we will use mean, standard deviation, then interquartile range, then we will use quantiles. This one we will use as normally. Okay, so what are the values important will be 0.25, we will take 0.25, then we will take zero point 0.5, and 0.75 and 1. So what actually we are doing it here, we are creating the like so like mean, standard deviation, like this, all these things we are selecting from the both the datasets, main dataset and female dataset, male and female both datasets we are creating this. And based on that we will be creating the factors. So for this one, important values are 0.25, 0.5, 0.75 and 1, and we are clicking on OK. Once you click on this OK, you will get one values on the weight data. You can get it from here, it will be available here. So you can see for the males we have 78.18, like this, 78.14, like this, you have all this data here. mean and standard deviation, IQR 25%, 50%, 75%, 100%, and the total data set. So all these values, we think that these are very important to compare two data sets, and the same values we will again take for the female data set. So here we will select FDIMS, and in the statistics, then summaries, numerical summaries, and we will select based on weight. So weight, and in statistics, mean, standard deviation, interquartile range, then quantiles. So again, okay. Now you see two particular values will be here. That is mean, standard deviation, IQR, all these values you have here now. Now what to do with these values? So these values we will use to just compare. We will use these to compare with our actual values. Like we will use this to compare. We will create a table, and then on this table uh, we can just have a comparison, and why we have selected these values. So how many values we have selected here? 1 2 3 4 5 6 7 8 and 9. So based on that, you can just create a table like this. So insert table, 1 2 3 4 4 values, and here, okay, insert table, number of columns 4, and number of rows we need 9. Yeah, so it will create a something like this. So what you can do, you can just give 9 or 10 we need here. So one another, like for example here you will give the mean, and then median, sorry, mean, we are using mean, standard deviation, then IQR. So mean, standard deviation, IQR. Then for quantiles, we have quantiles values, then four quantile values, and then n value. N means the sample space. What is the sample space that we are using for this particular question? So how you can create this table? I will give one example, and you can take all the other values from there only. So this is the statistic parameter or something summary. So this is the statistic, and this is the female weights, or just to give WGT, this is the male weight. Now here you have the reason why you have included that. That is very important, that we will discuss it here. So we have what are the things we have taken? Mean we have taken, we have taken SD, we have taken IQR, that is interquartile range, we have taken minimum, that is 0%, that is 0%, 25%, 75%, and 100%. So that is 0%, then we have 25%, then we have 75%, then we have 100%, and we have the n, sample space value. For example, I will just give what you need to do here. In the main section, just to go to your R command and take both the means. So this is for mdims, so this is the fdims mean. Copy it from here and paste it in the male weight section. And for female weight, again the same thing, female mean, that is 60.600 something. Just again we have to paste it here. So this is how we will be completing this table. So I am not going to complete this whole table again. You can just take the values from your R command and you can fill up this table. If you face any problem, you can comment it. I can maybe sort it out if I have time. So what this mean is doing, mean is it is showing average weight for comparison. So you can just pause this video and take the note whatever I am saying in the reason section, what you need to follow or what you need to give, and you can give it accordingly. For just one I am giving the example. So this shows average weight for comparison. Now for the standard deviation, why we are taking it? So it is basically standard deviation we are taking, which measures spread among the mean. So on the mean, how much spread we have, that we determine from the standard deviation. So that's why on the data set, on the summary statistics, we need to include the standard deviation also. Next, we have included the IQR. So for this IQR, this also spreads the middle 50% robust to outliers. This gives us a idea which shows spread of middle 50%. So that we have given, and then we have 0%, 25%, 75%, 100%. This 0% defines the lower end of the weight range. 25% is lower bound of middle 50% used for IQR. 75%, this is the upper bound of middle 50%. This is the upper bound for middle 50% used for IQR. And this 100% defines the upper end of the weight range, and the end it is indicating the reliability of the statistic, sample size, whatever you call it. So this is why we have selected all these parameters or all these statistics summaries. And the reason we have to write it here, the values we need to take it from here in our this chart. We need to take these values from here. So this is how we can complete this 18th slide. Now coming to the 19th slide question. So eyeballing the shape of the histogram is one way to determine if the data appear to be nearly normally distributed, but it can be frustrating to decide just how close the histogram is to the curve. An alternate approach involves constructing a normal probability plot, also called a QQ plot, for quantile for the female data. So on the female data, this has already been created. We just need to formulate the same for male data. So a data set that is nearly normal with result in a probability plot where the points closely follow the theoretical line. Any deviations from normality leads to deviations of these points from the line. Next part, create and paste QQ plot for the quantile for the male data. Here you can see it has been created for the female data, and now we have to create the same for the male data also. So 3C completed. We are now moving to 3D. So in the 3D, first we will see what this one is doing. So let's see first what it is doing here. This command, what it will do, what we are currently doing on the female data set height. So we are just giving here one command already created. So this is normal QQ plot. If you want to change the name, you can add it here. That we will do while we will be doing the male data set on the male data set operation. Now next what it is doing, that is QQ line deviation. It is just taking, so we will push it again. So what it is doing again, on the graph you can see one line has been created. Now the same thing we have to do for the male data set. So what we will do, come here again, and again what it is asking, create and paste a QQ plot for quantile for the male data. So now we are working on the male data. So for this one also it is very simple. We will use the same formula or the same functions just we have used for the female data set, and we will create it here. But as you have seen, if you want to give the you know a title of the graph, then how you can do that, I have already shown that you can use the main attribute or the main argument. So I'm just giving the main argument, that is main equals to, we're just giving the title. So that is main heights QQ plot. So QQ plot for mains height, or we can give best MDims. Now we can create this, and we will see QQ plot for MDims created. Previously it was normal QQ plot, something like that. Now we need to, sorry, this should be 1 minute. This should be MDims. Okay, this should be MDims because we are doing it on male data set. So we need to close it. We have closed that, and again we will give, so this is on mains dataset, and we will give the QQ line also on the mains dataset, that is MDims. So again enter, and we have this ready. So this line also gets created. Now again save as PNG, and that is QQ. We will just keep QQ on MDims. So saving this, and we will give the commands also. In our case we will give the commands, and then so both are here. and we will just give it, this is the command, and the separator is here, QQ line, right? So this has been created. We will just make it a little bit big, 12, and we will import the image also, pictures, this device, QQMDIMS insert. So this is also created, done. This part is also created. Now coming to slide number 21. So what it is telling, let's perform a test of normality SW for the male and female datasets separately. We will use the normality test function in the RCMDR MISC package. Already this package is installed when you install through the dependency that I have shown the first of this video. So if you go there, you can see how we have installed. In the packages section, you will already see that RCMDR miscellaneous, sorry, MISC is already running. So no need to again just import this package or import this library, no need to do that, it's already there. So you will use the normality test function in the RCMDR package, start by activating the, so it is showing to activate, but we don't need to activate it because it is already activated. Now coming here, what it is asking, the for the male data, create a new variable containing the male height data. So for the male data, we need to create a m height. So let's do and create a m height here. So if you see here in this section, the m height will be created. So we are creating this m height here, and you will see the m height is created here. That is, it is taking obviously 247, and for female it will take 260. Okay, so male height is created. So the now on this p value only, the most important part will be there. And again, after taking this m height, there is another one thing also given, that is normality test, m height test, then Shapiro test. You can do it in both the ways. You can take the Shapiro test values from, let me first run this. We will do it from both GUI and from command. So first I'm running this, and you will see the Shapiro Wake normality test values are given here. Same thing you can do on the, in which dataset we are doing it, in the male dataset MDIMS. So you can do it from here also. Come here and then select the dataset on MDIMS, and on the statistics, summaries, test of normality, Shapiro Wilk, and based on what? Based on height we are doing, click on OK, and you will get it again. See, in both the cases the result will be same obviously, but these are both the ways you can perform. One way that is mentioned in the PPT, normality test, which will be taking the package from RCMDR miscellaneous, and the second one you can do it from directly RCMDR commander or R commander. There you need to go to the yeah, statistics summary, then test of normality. From there you can take these values. So here you can see W equals to 0.99358 and p value is 0.3716. Here the point comes, what you need to do it here. So in this section on the normality test, so the data, and you can confirm this data, it is already given also. See, m height W equals to 0.99358, match it here 0.99358, and p value is 0.3716, match it here, p value is 0.3716. So definitely it is as it is. So what is the question here? This all are done, this all are given. So interpret this result. Are this data normal? Why or why not? So what you need to do, just duplicate this slide and then delete everything from here and write your answer. What you think on the previous data? Everything is already calculated, but we have again calculated and we have just matched the values. Now what in the question it has been asked, that are the data normal? So that only we are doing it here. So I think the most important part will be here to understand what we are doing it here with the hypothesis values. So if p value is greater than 0.05, we fail to reject h naught. So data is consistent with normality, right? So So for this one, the test evaluates whether there is sufficient evidence to reject or not. The decision rule is based on the p-value. So if we go, this is the p-value. The decision is based on this p-value. Now you can just from this video only, you can just take the text and you can give it here. So for the male data, the answer mainly we need to understand the p-value. So if the p-value is greater than 0.05, we fail to reject H naught. If the p-value is less than equals to 0.05, we reject H naught. So based on this p-value, so first is you write about the p-value. So here first we need to write about the p-value or the write the hypothesis. So write the testing. On this testing, on the H naught value, what is null hypothesis testing? We all know. In null hypothesis testing, first we need to provide if p value is greater than 0.5, what happens? If p is greater than 0.05, what happens? And if p less than equals to 0.05, what happens? First these two we need to mention. So you can write for p greater than 0.05, we fail to reject H naught, and if p value is less than equals to 0.05, we reject H naught. So now if you see in this case the p value is 0.3716, which is uh, greater than 0.05. So we fail to reject the null hypothesis. This comes under this class here. This comes under here. So we have 0.3716, that is definitely on p greater than 0.05. So we fail to reject the null hypothesis. The W statistics of 0.99358, this W statistics 0.99358 that we have here, 0.99358, already P statistics we have given the description. Now coming to W statistics, on the W statistics, so this is the P value that you have to first mention. And now coming to W value, in the W value is close to 1, which indicates the data closely resembles a normal distribution. The W value is close to 1, W value is close to 1, which resembles the normal distribution. So indeed we can say that this is normal data, and also the sample size is big, 247. So result is reliable and there is no significant evidence of deviation from normality. So indeed it is a nearly normally distributed. So what we can say, yes, it's nearly normally distributed. Now only if you just write this is not enough. You have to just, in the video you can watch again, you can recap, and you can just write down whatever we have spoken till now. So this is the answer for male data. Now coming to do the same analysis for the female data. So again we have to do the same analysis for female data. So what we, again we will just create the same for female data, and both we will compare again. So this is m height, we will create a f height. So this is a f height with fdims height. So this is the f height created, right, on 260 data. 260, it was 247, this is 260. Now coming to the next part, that is a normality test on Shapiro test. So here normality test, this is f height, test is Shapiro, and this is the values. These are the values, same values we will again take it from our RCMDR. Now we will do it on FDIMS dataset. Statistics, summary, test of normality. What is the field? Height. Then Shapiro will test. Okay, see here we have given normality test on F5 test, Shapiro test. W value is 0.99283, 0.99283, p value 0.2437, p value 0.2437. Anyone you take, I will take this value. So this is the output from the females data. So we need to, yeah, do the same analysis for female data. So this is the, first of all, commands that we have used. Okay, so these are the comments we have used, and it is telling us again the same question. Whatever we have interpreted for the male data, we have to interpret for the female data also. So are the data normal? First of all, this question, so we have to go with p-value and w-value again. So if you see the p-value here, the p-value is 0.2437. So again I will just paste it here, and one by one we will see. So write the testing again, write the testing, and this one we will see, no problem. So on the testing value, so what is the value here? P value 0.2437, 0.2437. Definitely it is also greater than 0.05. So in this hypothesis, what is exactly we can conclude? That null hypothesis, the female height data is normally distributed. This is the null hypothesis. An alternate hypothesis, HA, is the female height data is not normally distributed. Based on the p-values, we can confirm. So yes, the female height data is nearly normally distributed. Why? Because the Shapiro-Wilk test p-value is 0.2437 that I have written here, which is greater than 0.05. So we failed to reject the null hypothesis that female data is female height is so we reject, so we fail to reject the null hypothesis that, so we are not able to reject that the female height data is not normally is normal, sorry, the female height data is normally distributed. This we fail to reject. This is the H naught. So that's why this is saying that yeah, this can be normal. Second one is the W value. The W statistics again is close to 1. You can see the W statistics value here, that is 0.99283, which is again close to 1, indicating the data closely resembles normal distribution. So with a sample size of 260, again it is a kind of big sample. So we can say that yeah, this is also normally distributed. So that's why this is again for the same, right, the testing, then like the hypothesis testing what you are doing it here, then here p values, and the same things again you have to write. So you can see this video, like recap this here in the mail data section, whatever we have given the description, same will be here, these values will be different. So both fdims and mdims on height will be normally distributed or nearly normally distributed. Now question number 25. It turns out that so it turns out all, so in the example, what is the probability that a randomly chosen male or female is taller than 6 feet 182 centimeter or more? We can find this probability by calculating a Z score and consulting a Z table, also called a normal probability table. In R, this is done in one step with the function p norm. So you can see already FAGT mean and FAGT SD is created, right? FAGT mean and FAGT SD is already created. Now we will see what this is giving the return, and we will try to match it with this value given in the question paper. So we are giving this and see 0.004434387, 0.004434387. Now note this calculation is for the female distribution only. Now coming to the function p norm calculates the area under the normal curve below a given value q with a given mean and SD. Since we are interested in the probability that a woman is taller than 182 centimeter, we use 1 minus that probability. So assuming a normal distribution has allowed us to calculate a theoretical probability, if we want to calculate the probability empirically, we determine how many observations fall above 182 and divide this number by the sample size. So this has been created here. So this has been done. Again, we will just run it here. This has been given for the female data set. So this is also 0.0038465154, and matching that 0.0038465154. Although the probabilities are not exactly the same, they are very close. The closer the distribution is to a normal, the more accurate the theoretical probabilities will be. Now the question is, calculate the probability that a randomly chosen male is taller than 6 feet. So we have to do this for male data set. So here if you see, the p norm values are given here. So p norm is already calculated, but again we will run it, no problem. We will just run it for the, and see MAGT mean and MAGT SD. Before running anything, just check it here, MAGT mean and MAGT SD, or whatever your variable or values, that should be there in the environment. So now we will run it here again on the male dataset or MDIMS. So that is 0.2768345 here, 0.2768345 exactly. And then next what we need to calculate, we need to calculate the sum of M height greater than 182 divided by length of M height. So this one we need to calculate on male dataset. So how we can do that? We can just give it here, and this is M height and this is M height. So again for 182 we just need to, so you can see here this is 0.2631579. Just give this here, just yeah, we need to just paste it here. So this is the calculated probability, and we can see that for this conclusion we can see that this is much the difference is not that much on the p-norm and the calculated, right? The difference is not that much. So this answer is also completed. Calculate the probability that a randomly chosen male is taller than 6 feet 182 centimeter or more. So this is the answer. We need to do it on M height. Already the answer has been given for F height. Same we need to populate it for M height. Now the last question of our assignment, which is for extra credit. Calculate the actual Z scores for the male and the female data. Briefly discuss how the values you calculated related to the probabilities are computed. So for this one, for Z score, we will be using the that 182, that value already provided here. Calculate the actual Z score for the male and female data. Briefly discuss how the values you calculated related to the probabilities of are computed. The whatever we have already computed, so that it is asking. So Z score for female data at height 182 centimeter. So Z score, let me do it here. So Z score for female data at height 182 centimeter, at height 182 centimeter. So what we will be using here, again same thing we will be using, that is we will be defining one variable here. So let's define it as z underscore female or anything, z underscore fdims female, anything, z underscore fdims underscore 182. So z underscore fdim underscore 182, we will be assigning this in 182 minus fhgt, means fhgt mean divided by fhgt sd, standard deviation. So this is created here 2.61 something, this value is created. See here fz dims, and if you want to see this value, just give it here and enter the values here. Now we will be creating same on male dataset. So mdims 182, then mhgt min, and then mhgtsd, and then we will give enter. So z mdims 182 is created, and if you want to see the value again in the console, just we need to give it here, and this is the value, the same value you can see here. So these two are created. So for the first part, just we need to take it zdims, this one till here, and we will z score for the female data set, we will give it here. This is the z score for the female data set. So this is the zdims value, this is done, given. Now for the z score for the male data set, so z score for the male data at height, so again we will take it from here. This has been created for male data and we will paste it here. So this is for male data. So we will take it here. So you can see both are there. Now we need to calculate the probabilities, pnorms. So we will do that now. So Z score is here for male. This one is for females. So we have it here. Done. Now what we need to do, we need to create the Z score probabilities in R. So probabilities, again text box, probabilities, I think. So in the probability section we will directly use 1 minus p norm here, right? So we can directly use that. So 1 minus p norm, and 1 minus p norm we will be using for the female data set, that is Z FDIMS 182. So you have this value, just take it, and this is your probability here. So this is the probability for females. This is the probability for females. So insert text box females, and so this is female probability, and for the male again we need to 1 minus p norm for male sections. So we'll just copy on the MDIMS data, we can do that. So males, and on the here we will use 1 minus p norm, this is Z minus MDIMS 182. We have the value, so we have here. So again you can take it, and that's done. So 1 minute. So this is also completed, and here this assignment gets completed. Now on the submission part. So males and females, all these extra credit, calculate the actual Z score for the male and the female data. So the actual Z score also completed on the 182 value. Briefly discuss how the values you calculated related to the probability. So how these values we have calculated, everything we have shown here. Sorry, so this is where your PPT gets completed. Now how to submit this? First save. There is one naming format that you need to follow, our assignment roll number .ppt. So just copy and file, save as, anywhere wherever you want, just save it, and roll number, that's it, this PPT. And you can submit by PDF also. So PDF also. So this is just simple. I know, like, this is very simple, but main part will be the R routines. So how to create the R routines also. This is how your assignment should look like. All these answers we have given for the time section, so that we have given small things here, but if you see this video you will get the complete data, what you need to give here, what needs to be done. So that's one thing. Now for the R routines you can do one thing. So you can install the Notepad++, okay, or any text editor, no problem. Then take this whole select all from your console, and then give here, select everything from your console and give here, and then save it as R routines, save as downloads, R routines, R routine, and then create R file. I personally prefer Notepad++, but anything whatever you like you can do that. So this is yeah, R programming language. So save it. So this is your R routine created. So in now download section, you have this R routine and this PDF, and then you just need to compress to zip file, and then that's your submission. So this you need to submit. So that's all. I think this completed all the uh, slides from the PPT as well as R routines. So upload the file along with supporting R routines on Google Classroom as a zip file. So this is completed. Thank you. If you have any query, you can comment. Thank you.